Hey there, and welcome to this epic historical explainer. Today, we're basically going to act as scientific detectives cracking the ultimate cold case, the hidden structure of our entire universe. We are going on a mind-bending journey through time to discover exactly how humanity figured out what everything around us is actually made of. It's a story completely packed with brilliant guesses, ignored geniuses, and shocking experiments that literally changed how we see the world. All right, let's lock in your mission objectives. We are going to trace the timeline of discovery, starting all the way back in ancient Greece and rocketing right up to the 20th century. Along the way, we'll break down the wildly different models proposed by heavyweights like Dalton, Thomson, Rutherford, and Bohr. We're going to master the evidence by looking at the exact groundbreaking experiments that prove these invisible particles even exist. And finally, you are going to absolutely ace the assessment in a high-stakes, rapid review at the very end. So here is the level map for our adventure today. We'll kick things off with the ancient guesses, move into Dalton's solid sphere, taste test Thomson's plum pudding, get shocked by Rutherford's gold foil, jump into Bohr's energy levels, and finish it all off with our boss battle final challenge. Mission 1. The ancient guesses. No experiments here, folks, just pure ideas. We're hopping in a time machine and traveling over 2,000 years back in time. Back then, hardcore scientific labs just didn't exist. It was all about intense philosophical debates in the town square. Right around 500 BCE, a philosopher named Leucippus threw out this wild idea of tiny, indivisible particles. Soon after, his student Democritus expanded on it, calling these tiny bits of matter atoms. But then, the incredibly famous Aristotle stepped in. He proposed that everything was actually made of just 4 elements. And because Aristotle was, well, a massive celebrity at the time, that brilliant early guess about the atom was basically ignored for 2,000 years. The debate wasn't even truly revisited until the 17th century by guys like Galileo and Newton. But the real turning point? That was the late 18th century, when Antoine Lavoisier, the father of modern chemistry, established the law of conservation of mass. He finally paved the way for actual mathematical proof. Let's put these two foundational ideas head to head. In one corner, we have Aristotle's super popular 4 elements theory, the idea that all matter is literally just combinations of water, earth, air, and fire. In the other corner, Democritus and Leucippus's atomos, the idea that matter is built out of tiny, invisible, and indivisible building blocks. Aristotle's idea was totally wrong, but everybody believed it. Democritus was largely ignored, but actually hit the nail on the head. So I want you to pause and really think about this for a second. Why on earth do you think people believed Aristotle's completely bogus theory for over 2 millennia? Well, put yourself in their shoes for a minute. Without modern scientific equipment, no microscopes, nothing, relying on your own human senses just made the most logical sense. You can feel water, you can see fire, you can touch the earth, you can breathe the air. Believing in some magical, invisible, tiny particles that you can't even see, that just sounded completely ridiculous to them. Mission 2. Dalton's solid sphere, the very first scientific model. This is the exact moment where hard science finally catches up to ancient philosophy. John Dalton steps up and completely changes the game after 2,000 years of waiting. He gave atomic theory its actual scientific backing by laying out 4 crucial rules. Rule 1. Elements are made of extremely small, indivisible building blocks called atoms. Rule 2. All atoms of a given element are exactly identical in size, mass, and properties, kind of like identical twins. Rule 3, and this one is huge, compounds are formed by combining atoms of different elements in simple, fixed integer ratios. And Rule 4, chemical reactions only separate, combine, or rearrange atoms. They absolutely never create or destroy them. We call his concept the solid sphere model because it finally provided the mathematical backing for how atoms lock together in those fixed ratios. Let's make sure we lock in exactly how Dalton defined the atom. For him, an atom was an extremely small, completely indivisible building block of matter. He took that old-school term atomos from Democritus and permanently cemented it into modern science as the universe's ultimate, solid, totally unbreakable unit. But hey, here's a fun question to test your thinking. If Dalton truly believed atoms were just tiny, perfectly solid balls, what do you think he would say about the complex atomic models we use today? Honestly, his jaw would probably drop. He'd be utterly shocked to find out that atoms aren't solid and indivisible at all, but are actually full of incredibly complex, tiny moving parts. Which brings us to Mission 3, Thomson's plum pudding. Wait a minute. Atoms are divisible. Get ready, because J.J. Thomson is about to completely shatter Dalton's fundamental rule. He ran this wild, groundbreaking experiment using a cathode ray tube. He pumped voltage into gas inside a low-pressure tube, and boom, he saw a glowing beam shooting from one end to the other. He realized this beam was actually made of tiny particles with a negative charge, which he called electrons. Now, because atoms are electrically neutral overall, Thomson logically deduced there had to be some sort of positive charge in there to balance out those negative electrons. So he pitched the plum pudding model, a positively charged sphere, that's the pudding, with negatively charged electrons, the plums, scattered all throughout it. Let's quickly define this game changer. An electron is a nearly weightless subatomic particle with a -1 charge, officially discovered by J.J. Thomson. And you know, discovering this specific little particle wasn't just a win for chemistry textbooks. It was literally the key to unlocking modern electricity. It's the whole reason we can harness efficient, clean energy sources today. Now I know plum pudding is a very British, very 19th century reference. What modern foods can you think of that have small pieces scattered throughout, just like Thomson's model? The absolute best visual analogy to lock this into your brain forever is a chocolate chip cookie. Think of the soft dough as that positively charged sphere, and the chocolate chips as those negative electrons scattered all over the place. Mission 4, Rutherford's gold foil. This is the experiment that literally shocked the world. Before I spoil the surprise, I want you to make a prediction. If you were to fire heavy, fast-moving, positively charged alpha particles directly at Thomson's soft pudding atom, what should logically happen? Well, if the atom is just a soft, spread-out cloud of positive dough, those heavy, fast bullets should just punch straight through it like it's absolutely nothing, right? Well, the reality was mind-blowing. Ernest Rutherford set up a detecting screen around an incredibly thin sheet of gold foil. And sure, while most of the alpha particles did cruise straight through exactly as expected, a tiny, tiny fraction of them deflected off to the side, and a very small number bounced almost straight back. He said it was like firing a massive artillery shell at a piece of tissue paper and having it bounce back and hit you. No way, right? Rutherford realized 3 massive things. First, since most pass through, the atom has to be mostly empty space. Second, since a few violently bounced back, there must be a tiny, incredibly dense, positively charged center repelling them. And third, those electrons must be revolving around that center at insanely high speeds. And just like that, a brand new term entered the dictionary: the nucleus, the extremely small, dense, positively charged region at the absolute center of an atom. To really put that scale into perspective, if an atom was a massive, sprawling sports stadium, the nucleus would be a single, tiny marble sitting dead center on the 50-yard line. It is that tiny, yet it contains almost all of the atom's mass. Mission 5, Bohr's energy levels. Time to fix the flaws in Rutherford's orbits. So Rutherford's model had a major physics flaw. Why don't those orbiting electrons just lose energy and crash directly into the positive nucleus? Enter Niels Bohr with the Planetary model. He figured out that electrons can't just orbit anywhere they feel like. They are restricted to specific, defined, quantized energy levels. These are set distances from the nucleus, with absolutely no in-between allowed, kind of like planets orbiting the sun. Even cooler, he proved that if an electron absorbs energy, it jumps up to a higher level, and when it drops back down, it releases that energy by shooting out a photon of light. This jumping behavior perfectly explained the totally unique, distinct colored lines scientists were seeing in the hydrogen emission spectrum. Bohr basically mapped the atomic orbits. And here we are, Mission 6, the boss battle final challenge. Let's synthesize the evolution of the atom. You have successfully navigated over 2,000 years of scientific discovery. So let's synthesize everything we've cracked so far. First, John Dalton gave us the solid sphere model, showing that atoms act as indivisible building blocks combining in fixed ratios, just like a solid billiard ball. Then, J.J. Thomson gave us the plum pudding model, discovering the negative electron and proving atoms actually are divisible, perfectly visualized as a chocolate chip cookie. Next up, Ernest Rutherford gave us the nuclear model, discovering that tiny positive nucleus and proving atoms are mostly empty space, like a marble in the center of a massive stadium. And finally, Niels Bohr gave us the planetary model, discovering quantized energy levels where electrons jump past, just like planets orbiting the sun. Let's lock this case file in with a 60-second rapid review. Ready? Aristotle's four elements ruled for 2 millennia while Democritus was totally ignored. Lavoisier, the father of modern chemistry, proved the law of conservation of mass. Dalton finally gave atomic theory hard scientific proof. Thomson discovered the negative electron using a cathode ray tube. Rutherford discovered the positive nucleus using a sheet of gold foil. Bohr proved electron energy is quantized, which creates light spectra. And above all, never forget that a stable atom is electrically neutral. It always balances its positive and negative charges. We made it to the final challenge. I want you to pause this explainer right now and see if you can answer these 5 questions using only your memory. If you can remember who established the conservation of mass, which model states atoms are identical, what those alpha particles bounced off of, what subatomic particle Thomson found, and why Bohr's hydrogen spectra are so important, then you have truly mastered the case file of the atom. As we wrap up, I want to leave you with a thought. If our understanding of something as fundamental as the atom went from a perfectly solid sphere to a crazy, complex, highly energetic solar system in just one single century, what on earth do you think scientists will discover about the universe in the next 100 years? Keep questioning, keep learning, and I'll catch you in the next explainer.